Generation of PN sequences or pseudonoise sequences. The contents of today's discussions are listed here. The first topic is pseudonoise, that is PN, pseudonoise sequence. What exactly pseudonoise sequence is and the introduction to it. And the second topic is general M stage shift register with linear feedback. This is one method of generating pseudonoise sequence. So we'll be discussing about that in detail. The third topic is shift register connections for generating maximum length sequence. For different length of maximum shift registers, the connections are different. So we'll be discussing about that. And the fourth topic is maximum length code generation. We consider one length and length of the sequence, and we generate or we discuss about the generation method of maximum length code sequence. And the last topic is properties of maximum length sequence. Mainly we have three properties of maximum length sequence. The first one is balance property, and the second one is run property, and the third one is correlation property. We'll be discussing about all these properties in detail here. And at last we'll be solving one problem that is related to properties of maximum length sequences. The first topic is Introduction to Pseudonoise or PN sequence, or what exactly pseudorandom or pseudonoise sequence is. A pseudorandom or pseudonoise, that is PN sequence, is a code sequence of ones and zeros whose autocorrelation has the properties similar to those of white noise. A pseudorandom or pseudonoise signal is not actually a noise signal. If anyone knows about the generation pattern of pseudonoise or PN sequence, it is nothing but a pattern of zeros and ones which repeats after a long duration. If not, it is nothing but a random or noise kind of signal. The most widely known binary pseudonoise or PN code sequences are the maximum length shift register sequences, which we will be studying later. The next topic is M stage shift register with the linear feedback. The figure shows the shift register of M stages with linear feedback. Here some stage outputs are XORed, that is modulo 2 addition is performed and given as input to the first stage. And after 2 to the power m minus 1 stages shifts, we get the maximum length sequence. A maximum length shift register sequence or M sequence for short has a length that is L is equal to 2 to the power m minus 1 bits. That means, for example, if m is equal to 3, that means the number of stages present in the shift register is 3, then the maximum length sequence generated out of it, that is L, that is equal to 2 to the power m minus 1. That means 2 to the power 3, that is equal to 8 minus 1, that is equal to 7. So in this case, if m is equal to 3, that means the number of stages in the shift register is 3, then the maximum length sequence generated out of it will be having a length of 7 and is generated by an M stage shift register with the linear feedback as shown in the figure. And the second point is the sequence is periodic with the period L. That means the maximum length sequence generated will repeat after a period of L. In the previous example, if you consider, it repeats after a period of 7. The next point is each period has a sequence of 2 to the power m minus 1 ones and 2 to the power m minus 1 minus 1 zeros. That is, if L is equal to 7, that means if the length of the sequence is 7, in that case m will be equal to 3. That means 2 to the power 3 minus 1, that is equal to 7. So if L is equal to 7, m is equal to 3. In that case, in that particular sequence, the number of ones will be 2 to the power m minus 1. So that is 2 to the power 3 minus 1. That is 2 to the power 2. That is equal to 4. So 4 number of ones will be there, and 2 to the power m minus 1. That is 4 minus 1. 3 number of zeros will be there. So that means if the sequence length L is equal to 7, in that case 4 ones and 3 zeros will be present. The next topic is the shift register connections for generating maximum length sequences. In the previous section, we have seen the diagram, that is general M stage shift register with the linear feedback. Here, this particular table explains for a given number of shift register stages, that is, if M is given, what are the shift register stages should be connected to modulo 2 adder. That is, if you just look into the table, that is to generate maximum length sequence of 2 to the power 2 minus 1, that is 3. 2 to the power 2 is 4, minus 1 is 3. That means if m is equal to 2, we can generate a maximum length sequence of length 3. For that, the stages connected to modulo 2 adders are 1 and 2. That means the first shift register output and the second shift register output should be connected to modulo 2 adder, and the output of the modulo 2 adder should be connected to the first shift register. Similarly, if m is equal to 3, that means if 3 shift registers are present, that means to generate a maximum length sequence of L is equal to 2 to the power 3 minus 1, that is 8 minus 1, that is equal to 7. That means to generate a maximum length sequence of 7, we should use m is equal to 3. In that case, the stages connected to modulo 2 adder are 1 and 3. That means the first shift register output and the third shift register outputs should be connected to modulo 2 adder, and the output of that should be connected to the shift register 1. Similarly, if m is equal to 4, the stages connected to modulo 2 adder are 1 and 4. That means the first shift register output and the fourth shift register output should be connected to modulo 2 adder, and the output of that should be connected to the shift register 1. And if you see the table here, if m is equal to 8, the stages connected to modulo 2 adder are 1, 5, 6 and 7. That means if m is equal to 8, the output of the first shift register output, the fifth shift register output, the sixth shift register output and the seventh shift register output, so that should be connected to modulo 2 adder, and the output of that should be connected to the first shift register. And similarly, so we can get the stages connected to modulo 2 adder from this particular table for the different values of m. The next topic is maximum length code generation. The figure shows the maximum length code generation procedure for m is equal to 3. That means when 3 shift registers are used as shown in the figure. If you just look into the block diagram, it uses 3 shift registers, shift register 1, 2 and 3. And one more observation what we can have here is all are connected to a same clock. Since here m is equal to 3, that is the number of shift registers used are 3, the length of the sequence, the maximum length sequence generated out of it, so that will be L is equal to 2 to the power m minus 1. So that means L is equal to 2 to the power 3 minus 1. So 2 to the power 3 is 8 minus 1, that is equal to 7. So with this arrangement, we can generate a maximum length sequence of length 7. And one more important observation what we can make here is, since m is equal to 3, that means the number of stages included here in this shift register in this arrangement is 3. So The shift register 1's output and shift register 3's output are connected to modulo 2 adder, and the output of it is connected as input to shift register 1. This is as per the representation given in the previous table. And the very important thing we need to consider in the construction of maximum length code generation. Now let us look into the working of this maximum length code generator. Now let us consider the initial value at the input of each shift register. Let it be 1 0 0. That means at the input of the first register the value is 1. The input of At the input of the second register the value is 0, and at the input of the third shift register it is 0. Here one important thing we need to consider is the value should not be 0 0 0. That means the at the input of all the three shift registers the value should not be 0. Now let us consider the value as 1 0 0. When we apply the clock pulse, since the same clock is connected to all the shift registers, when we apply the clock pulse, the output of each shift register, if you just if you just consider for the given input, it will be 1 0 0. Now if we just look into the output of the shift register 3, the value is 0, and this is nothing but the first value of the pseudonoise sequence, that is 0 here. But at the same time, one thing we need to observe, that is the output of the first register is 1 now, and the output of the third register is 0. So now here the modulo 2 addition, that is XOR operation, is performed between the output of shift register 1 and the output of shift register 3, that is 1 and 0. The output is 1, that is given as input to the first register. Now when we apply the second clock pulse, now what happens is the first shift register output will be 1, the second shift register input previously it was 1, so now it shifts to output, so that is also 1, and the third shift register output will be 0. So now the second the pseudonoise sequence bit is the output of third register here, that is again 0. But at the same time the first shift register output is 1 and the third shift register output is 0. So the XOR operation takes place between these two. The output is 1, that is again given as input to the first shift register. So now if we apply the third clock, so the output of the first shift register will be 1, the output of second shift register will be 1, and the output of third shift register will be 1 again. Now the output of the third shift register is 1, and that is nothing but the third bit in the pseudonoise sequence. But at the same time the output of the first shift register is 1 and the output of the third shift register is also 1. So if you perform the modulo 2 addition between these two, that is XOR operation, the output is 0. So now 0 is fed into, or 0 is given as input to the first shift register. Now if you apply one more clock, now the output of the first shift register will be 0, the output of second shift register will be 1, and the output of the third shift register will be 1. So now the output of the, since the output of the third shift register is 1, the fourth bit in the pseudonoise sequence will be 1. But at the same time output of the first shift register is 0 and the output of the third shift register is 1. So the modulo 2 addition between these two gives the output as 1 again. So this is given as input to the first shift register. So now if we apply the clock signal, the output of the first shift register will be 1, the output of the second shift register will be 0, and the output of the third shift register will be 1 again. So now the output of the third shift register is 1, so the fifth bit of the pseudonoise sequence is 1 again. Like that, after 7 shifts, the pseudonoise sequence, what we get is 0 0 1 1 1 0 1. And after that, if the process is repeated, the same sequence repeats. That means the length of the sequence is 7. After that it repeats again. This is the process of maximum length code or sequence generation. Here the number of shift registers are considered and that is equal to 3, that is m is equal to 3. So the length generated is L is equal to 7. If m considered, if it is equal to 5, in that case what happens is m is equal to 5, that is 2 to the power 5 minus, that is 32 minus 1, that is equal to 31. So that means the length of the sequence will be 31 and it repeats after that. And one more important thing is, in that case after the shift register 1, the output of shift register 1 and shift register output 4, that should be considered for modulo 2 addition, and output of that should be connected as input to shift register 1. This is one important arrangement we need to consider. The next topic is properties of maximum length sequence. The maximum length sequence have the following properties. The first property is balance property, the second property is run property, and the third property is correlation property. So if you consider the first one, that is balance property, in each period of maximum length sequence, the number of ones is always one more than the number of zeros. For example, if L is equal to 7, that means the length of the sequence, length of the pseudonoise sequence, if it is equal to 7, in that case, the number of ones should be one more than the number of zeros. That means the number of ones should be 4 and the number of zeros should be 3. That is nothing but the balance property. The second property is run property. What exactly it explains is, among the runs of ones and of zeros in each period of a maximum length sequence, one half the run of each kind are of length 1, 1/4 are of length 2, 1/8 are of length 3, and so on, as long as these fractions represent meaningful number of runs, and the total number of runs is equal to n plus 1 by 2. That means if the length of the sequence is 7, in that case the total number of runs will be 7 plus 1, that is 8 by 2, that is equal to 4. That is the run property. The third important property is the correlation property. It states the autocorrelation function of a maximum length sequence is periodic and binary valued. So which is usually defined in terms of the bipolar sequences Cn, that is here 1 is represented as +1 and 0 sequence or 0 bit is represented as -1, as RC of m, that is equal to summation n is equal to 1 to L Cn into Cn plus n, where m is nothing but the shift here, where m lies in between 0 to L minus 1, where L is the period of the sequence. Since the sequence Cn is periodic with the period L, the autocorrelation sequence RC of M is also periodic with the period L. Ideally, a pseudonoise sequence should have an autocorrelation function that has correlation properties similar to white noise. That is, the ideal autocorrelation sequence for Cn is RC of 0 is equal to L. That means if M is equal to 0, that means without shift, it is equal to L itself. And RC of M is equal to -1. So if for other values of M except 0, for other values of M, it is equal to -1 for M in between 1 to L minus 1. So this is the important thing we need to remember here in the correlation property. So in the case of M sequences, the autocorrelation sequence is RC of M is equal to L if M is equal to 0, that means without shift, and it is equal to -1 for other values of M, where M lies in between 1 to L minus 1. This is the important thing we need to remember. Now let us consider one problem that is related to the properties of maximum length sequence. The problem statement is consider a binary sequence that is 00111101 and check whether the given sequence satisfies the properties of maximum length sequence. Now the data binary sequence is given, that is 00111101. We have to check whether this particular data or satisfies the properties of maximum length sequence. If it satisfies the properties of maximum length sequence, we can say the given binary sequence is nothing but the maximum length sequence. Now let us start with the first property, that is balance property. Let us check the balance property. The given sequence is 00111101. The number of zeros in the given sequence is 3, that we can see here, and the number of ones in the sequence is 4. So that means the number of ones is 1 more than the number of zeros. So that is what the balance property says. So hence we can say the balance property is satisfied. Now let us check the run property. The given sequence is 00111101. So as per the rule, there should be 4 runs, because since L is 7 here, M should be 3. So the number of runs should be equal to 2 to the power M minus 1. So that is 2 to the power 2 minus 1. Sorry, 2 to the power 3 minus 1. That is 2 to the power 2, that is equal to 4. There should be 4 runs. If you just look into the sequence here, there are 4 runs in the given sequence, as 0 0, that is 1 run, 1 1 1, that is 1 more run, and 0 is one single run, and 1 is one more single run. So 0 0 is 1 run, 1 1 1 is one more run, 0 is 1 run, 1 is one more run. So here 1/2 the runs are of length 1, that is 0 and 1. So totally 2 out of 4, that is 1/2 of the runs are of length 1, and 1/4 are of length 2, that is 0 0 is of length 2. Okay, that is 1 by 4, 1 out of 4. So 1/4 are of length 2. And since the number of runs in the sequence is 4, we can ignore the run with the length 3. So hence we can say the run property is satisfied. Now let us check the correlation property. The autocorrelation property says RC of M is equal to L when M is equal to 0, that means no shift, and it is equal to minus 1 when M lies in between 1 to L minus 1, so that means other than 0. The given sequence is 00111101. If you just look into this, the sequence length is 7, that means L is equal to 7 here. Here 0 is represented as minus 1, or we should represent 0 as minus 1, and 1 is represented as, or we should represent it as plus 1. So when M is equal to 0, that is without shift, when there is no shift, the autocorrelation is represented as per this representation here. Okay, and with this what we can say, ultimately the value is equal to 7. Since L is equal to 7 in the given sequence, it satisfies the first part of the equation or the rule, that is RC of M is equal to L, that is equal to 7 when M is equal to 0. That means when there is no shift. When M is equal to 1, that is when there is one shift, when there is one shift, the autocorrelation is given here, that is Cn is multiplied with the Cn plus 1 for each shift, and ultimately we can say the value is minus 1. That is, it satisfies the second part of the equation, that is when RC of M is equal to minus 1 when M is not equal to 0. That means for other values of 0 between 1 to L minus 1. It satisfies the second part of the equation. So hence we can say it satisfies the autocorrelation property also. That means it satisfies all the 3 properties of maximum length sequence.